Dear students, welcome to the problem solving session on Milne Thomson's method part 6. In the previous video, we learned the basics how to tackle the problem if you get a problem in terms of the linear combination AU plus BV is equal to sum phi of x comma y. In this session, we are going to solve few problems on this combination. Let us have a quick recap. If f of z is analytic function, then if a and b are any real constant, a plus ib into f of z is also analytic. The reason is constant functions are analytic everywhere. Product of two analytic functions is always analytic. Therefore, a plus ib into f of z is analytic. If the problem is given in terms of a linear combination au plus bv is equal to some function phi of x comma y, to find the analytic function f of z is equal to u plus iv, we are going to use the method 1. So we can convert the problem as always real part. To achieve this, first take the coefficient of u and multiply with f of z. So we get au plus I into av. Next we have to take the coefficient of v, that is b, and always multiply with minus I, that is minus ib. Now multiply this minus ib with f of z. So we get minus I bu minus ib into iv is going to be minus I square bv. I square is minus 1, so minus into minus plus, we get BV. When we add these two equations, we get A minus IB into f of z is equal to AU plus BV plus I into AV minus BU. So always the given question will be the real part of the analytic function A minus IB into f of z. Since f of z is analytic, this A minus IB into f of z is also analytic. So we take this as capital F of z and AU plus BV as capital U, AV minus BU as capital V. And according to our given problem, U is equal to AU plus BV. Let us solve a simple problem. Given 3u plus 2v is equal to y square minus x square plus 16xy. I want to find the analytic function f of z is equal to u plus iv. So step 1, write the given question and we write f of z is equal to u plus iv. So now the coefficient is very important. So multiply 3 with equation 1. We get 3 into f of z is equal to 3u plus I into 3v. Similarly, now multiply equation 1 with minus 2i. As I said, when we go for the coefficient of v, take the coefficient of v and multiply with minus I. So minus 2i into equation 1, we get minus 2i f of z minus 2i u. Already we have iv. When I multiply with minus 2i, I'll get minus 2i square, that is minus 1 into v. So we get minus into minus plus 2v. Therefore, minus 2i into f of z is minus I into 2u plus 2v. If you add this both, we get 3 minus 2i into f of z is equal to the real part is 3u plus 2v plus if I take this I, we get 3v minus 2u. If some non-max students have some difficulties getting this equation, a simple idea, if the problem is given as 3 plus 2v, just write 3 minus 2i into f of z. Therefore, my real part will be the same, we'll get the same question, 3u plus 2v plus I into. Now interchange u and v and then you check the sign. If you have plus here, put minus. If you have minus here, similarly put plus. So now we have 3v minus 2u. You can check with the answer. Similarly, suppose if you have a problem like 2u minus v is equal to some function g of x comma y. How to express this? So I can write this as 2 plus I because I have minus here. So 2 plus I into f of z is equal to 2u minus v plus I into, I have to exchange u and v. So I will write 2v and u here. Since we have negative here, we can put positive. And then we can take this as capital F of z is equal to capital U plus I into capital V. Since 3 minus 2i is analytic and f of z is analytic, product of two analytic function is also an analytic function. I am going to assign this as capital F of z. So capital F of z is equal to capital U plus I into capital V, where capital F of z is 3 minus 2i into f of z. Capital U is 3u plus 2v. capital V is 3V minus 2U. Now we can see this 3U plus 2V is the real part of capital F of Z. That is nothing but the real part of 3 minus 2I into F of Z. So we are going to assume U equal to 3U plus 2V, that is equal to my question y square minus x square plus 16xy. After this, it is very important to mention that since f of z is analytic, capital F of z is also analytic. Then only we can able to proceed the further steps on Milne Thomson method, because we have to say capital F of z is analytic. After converting into this, we have to proceed as usual. Step 2. So instead of small u, now we have capital U. So we have to proceed everything in terms of capital U. So write capital U, find capital Ux. Differentiating capital U partially with respect to x. First term is 0, second term minus 2x, plus third term we get 16y. Similarly, capital Uy is 2y plus 16x. As usual, replace x by z, y by 0. So we get capital Ux of z comma 0 is minus 2z and Uy of z comma 0 is 16z. So up to converting this step is very important. If you find this capital U, after this problem going to be very simple. Next, step 3. Since the problem is real part, we know that capital F dash of z is capital Ux of x comma y minus I into Uy of x comma y. By Milne Thomson's method, we say this is equal to Ux of z comma 0 minus I into capital Uy of z comma 0. That values are readily available from step 2. So my capital F dash of z is minus 2z minus I into 16z. Now let us take this minus 2 and z in common. So we get minus 2 into 1 plus 8i into z. This is my capital F dash of z. Now integrating this capital F dash of z, we get capital F of z. On the other side we have integral minus 2 into 1 plus 8i into z dz. That is nothing but minus 2 into 1 plus 8i into z square by 2 plus constant c. Now I can cancel this 2. Therefore, my capital F of z is minus 1 into 1 plus 8i z square plus c. And many students will do the mistake. After this step, they will stop. They think that they find the analytic function, but we found the analytic function capital F of z. Capital F of z is my assumption, but according to the question, I have to find small f of z. You can see the typed version. We know the relation capital F of z is 3 minus 2i into small f of z. So now just substitute this here. So we get 3 minus 2i into small f of z is equal to minus of 1 plus 8i into z square plus c. So I want to find small f of z. Just divide by 3 minus 2i. So minus of 1 plus 8i divided by 3 minus 2i into z square. Since c is a complex constant, if we divide by another complex constant, simply we say this as c1. Usually we will not keep the complex number in the denominator. So we are going to multiply and divide by the conjugate of 3 minus 2i which is present in the denominator. So the conjugate of 3 minus 2i is 3 plus 2i. So we are going to multiply and divide by 3 plus 2i. We know that a plus ib into a minus ib is simply a square plus b square. So 3 minus 2i into 3 plus 2i is 3 square plus 2 square. That is 9 plus 4, 13. So my denominator is done. For the numerator, we have to multiply minus of 1 plus 8i into 3 plus 2i. I will just keep the minus as usual outside and multiply the remaining terms. If we multiply with 1, we get 3 plus 2i. If we multiply with 8, we get 24i. Then 16, I square is minus 1. So I'm writing directly minus 16. So it is nothing but 3 minus 16 as minus 13 plus 26i. Now we can take minus 13 in common, so we get 1 minus 2i. So minus into minus plus, therefore my numerator is 13, 1 minus 2i. My denominator is 13 into z square plus c1. Now I can cancel this 13, so we get small f of z is 1 minus 2i into z square plus c1. This is my final answer. So whenever you get a problem in linear combination, don't simply stop the problem with capital F of z. We have to find small f of z at the end. Hope you understand, students.
Thanks for watching. Hope you found this video helpful. Subscribe to our channel and share it to your friends. See you in the next video. Bye bye.